apart. There's nothing amazing in these pictures that I wanted to show you. I mentioned something about this picture, but mostly I thought that it's cool and dramatic, so I might as well. But I wanted to check with you. I'll give you anonymous feedback questionnaires that you can tell me things at this point of the course where we are past the half, but still I have a fair amount to go. And if you want me to change things. So I'll give you another channel to give me feedback, but I thought that maybe we'll chat about it Now, you want value adding by feedback. Think that you think that it's practical, that for the remaining of the semester, that you'd like to be different for whatever is left in the semester. Things that annoys you and are within my control. Just spit them out. Oh. Okay, I'll give you the anonymous channel. Unless I assume that everything is perfect, which requires some amount of optimism, but let's be more specific. Homeworks so far. Okay. You're saying most, if I understand your gesture correctly, it was mostly yes, but. So what's a but?
Labor intensive, but fair, I guess.
Theoretical, practical.
Theoretical.
Theoretical was
that last homework's theoretical part took significantly longer than the implementation of the code.
Okay, noted, and fair enough. I don't remember questions there that requires lots and lots of writing, but I remember. But it was a fair amount of questions. So yeah, noted. Other things about the homeworks? I mean, okay. Midterm, you don't know the grades yet, and I think that I'll wait with the grades until Wednesday, where probably we'll have the makeup exam, but then you know your grade. But your impression so far? Okay. Nice. About shadows, remember to create a shadow, we are having two passes, one from the sun that estimates the distances, using it as a texture, putting this texture and applying this texture from the viewpoint, basically checking for each point, are you in the right distance from the sun, or is the sun in your direction see a shorter distance? It cannot be longer, but it can be shorter. But it asks for numerical problems because we just have these many bits to estimate the distance. So there will be issues of my estimated of the distance from the sun cause me to place points where they shouldn't be. They just have that many pixels. It's not really the distances from the sun, it's only among the rays, and it's not the same rays that you're creating, the same pixels that you're creating from the viewer point of view. Sun is here, the viewer is here, so it's not exactly matched. So there will be various aliasing problem, including because you don't have enough many bits and enough many samples. Now, GSLS, the OpenGL, is much stronger in this case than WebGL. It allows you to define a buffer only for the depth. It allows you to say this buffer will have 32 bits, and then so it's more accurate. You can even define it as float, but it's still coming from just being integer numbers. So arguably that so far with quantum cards will not help. But mostly what it gives you is that it will be kind of anti-aliasing in OpenGL, but the aliasing is not based on just the standard aliasing of every pixel to look at its neighbor and create the distances. The aliasing would be, and because it knows that we are using the depth buffer to create shadow, distances would be from the sun. Let's ask what is the distance to our object here along this pixel pi. What would be the distance from the sun across this pixel? pi minus 1, and before it creates the shadow, here is one value, di minus 1. Here is another value, di, and before it decides about the shadow, it will assume that the actual object is diagonal over here. So it's linear interpolation of the depth that then you're using to decide a pixel is exposed to the sign or not. So stuff that OpenGL has and WebGL does not. WebGL, you just ask for every pixel, measure the distances, is this within the range, almost the sun object and a green object this way. I need to make the green object over here. This pixel is in the shadow because the distance that I have, di, is smaller than the distance to this object. So you need to check it, or your fragment shader checks it directly for every pixel. There are various shortcuts that you can see for WebGL, and if you want to study more, again, I recommend it several times. SEM, Uxel's, fantastic, absolutely fantastic, interactive computer graphics in Utah. They're valuable on YouTube. I sent a link somewhere. If you don't remember, just Google for YouTube for computer graphics, Utah University. Utah, I think, was, don't take me on it, I believe that Utah graphics alumni played a big role in pixel creation, but not entirely sure. Okay, and we are done with creating shadows. And to be honest, that's a slide that I got. I didn't remember why this is better than this, but they're both cool. Okay, yeah. Let's talk about reflection mapping and cube mapping and environmental mapping. They're all the same. So we have an object, liquid, metal, person, and there is an environment, and we want to create a reflection. You won't see it. The reflection of the pilot at the head of the liquid metal. You have to do something along this line in homework 6, where it will not be the simpler model. Maybe it would be liquid metal with ripples in it, but the idea would be the same. So the image of this pilot, the image of the environment stays for the next few frames, mostly the same. I don't need to change most of the frames for our discussion. Everything else is static except of the liquid metal guy that is moving and deforming. So, and we want to have a quick as this person is deforming. We want to generate quickly the reflection of it inside. And remember, everybody, here is a piece of mirror. Here is a ray that is coming, R, then here is R1, the ray that is reflected. What do you need to do to know what is R1? We discussed it many times. Let's remind ourselves. To know R1, what do I need to know? I first need to know P, where R hits the mirror, the surface. Then I need to know N, the normal at P. And then I added very simple formula that appears in the next slide that says once you know R and you know N, then you can also compute R1. We saw it in a few different ways. Sound good so far? So what are we going to do in this case? We are going to use cube mapping, described next, that will generate carefully and keep static. That would be like the image of everything surrounding the liquid metal guy, including the other pilot, and start to do to use our even Z buffer, but compute the reflection of every point in the liquid metal. So when there is a scene from a single point inside the reflected object, stored the rendered image, so I'll put a camera inside and rendered everything around it, treat it as a constant. It will also have application in billboarding, just billboards that are far, far away in the infinity. And now next, map texture from the first pass into the object. That's what we'll discuss next. So for each, what do I need to decide for each point of the liquid metal? I need to ask a point, a ray for this point, a ray that comes from the camera, hits this point, reflected in some direction that I need to compute, different for each ray, different for each point. For some direction, where does this other ray hit? You have to do it in homework 4 in a much simpler way with these two passes. Right, because it's a flat mirror, the mirror doesn't deform. If the mirror in homework 4 would have deformed, you'll have to do essentially the very same thing. So cube mapping, many applications, not only for the reflection. So I live in a world that has sky and bottom and walls and backside. So I'll imagine that I'm living in a cube, but the walls of the cubes are far, far away. And I want to place billboards there. But since it's kind of common process, I create the billboards of each one of the 6 faces, like 4 walls, top and bottom. I'll have a built-in mechanism that is called texture cube. And now, if you can just create the texture cube, you'll have to declare it earlier. You'll see in the next slide how. You'll have to assign 6 images with the texture cube. And now I can just do standard Z buffer with no reflection and other objects, and it will just show as the skies and the tree and objects at infinity. Why does it fit to be a billboard? Because if you are walking not a huge distance, the scene stays the same. Now, if you are, what's cool about this whole description is that if you are moving your viewing direction to the side or around the 4 walls, it will do it completely seamlessly. You will not see the boundaries between the 4 walls. But the same goes for the boundary between the floor and the walls. Right. That will all be handled by the WebGL out there. So you're just doing, you're asking what is the direction at some particular direction, dir here, direction is a vector, perform texture cube after the definition of the cube, and give it the name of the cube, again a collection of 6 images that sits right here, the direction, and it will spit out the color of this pixel. Exactly what you did in homework 2 for individual weight per individual billboard, now the gizmos of WebGL does it for you. And know already at which one of the 6 images to look for. So I just quickly copied for you. There are pieces that are missing, but I quickly copied how do you define the cube. Just the idea, I defined the creating, binding the texture to cube. Don't take my word here, do what I did, which is, of course, check GPT quickly, because I wanted to have quickly just this definition of referring to, provide the 6 images, right? Positive X, negative X, the back wall, positive Y, negative Y, the right and left wall, top and bottom, put whichever images that you want, and voila, you have the, and voila, you have, and you want to tell it that that's of course a cube texture. That's it. What do you do now if I created the whole scene minus the liquid metal? Again, I created as a texture cube the whole scene, which is static, minus the texture, minus the liquid metal person. Sorry, wrong direction. Now what I do, let's simplify it. I have a room, the texture of the 4 walls. I have an object in the center of the room, and this object is, say, a mirror ball. It's a mirror ball, just connecting it to this point. What do? I can use ray tracing, or I can just remember, hey, I know for a point my Z buffer, my fragment buffer, know what is the location and what's the surface of this location if I hit in the object. Now I need somehow to calculate, and your fragment programming, one of the cool things about fragment programming versus traditional Z buffers is exactly that they can do their own math, like compute what is the normal at this point once they know what's the point that I hit. Here is the formula that connects where the direction of that it's coming from. The normal and the direction that gives you the R, and takes the R and do look at for the color of the reflected ray. Make sense? That's a mirror. I'm just at the right place to see the red point of the mark 31. Shoot a ray, compute the ray, look at the ray's continuation. It hits the red digits over there. So I assume that that's the red point that I see over here. That's a pixel that my fragment returns. Yes?
That's a different equation that we got than what we previously used. Why is that? Before it was V minus 2 and V times N, or V dot N. But yeah, it's changed.
Equals 2 times.
The other one was negative, the same equation.
It's
Yeah, the other one is the opposite. Do you know one or an extra?
equal.
I guess he's subtracting
Right. So it's oh yeah. Yeah, that's the question is, do I assume that R1 is a ray that's going to hit, or I assume that V is the direction from this point to the viewer? R1 is a ray of light that comes from the viewer, V is the direction to the viewer. I think that that's a reason. I'll double check, get back to you.
No, that seems right.
Okay. Cool. So that's texture. So cube mapping, every time that you want to create the scenery of your nature, long things at the horizon, sea, sky, etc. It's a bit annoying that you need to provide 6 images. Yeah, just repeating, a bit annoying to provide 6 images. So you can always also use sphere mapping. You'll provide a pre-processed image, but only a single one. And what is this image that you provide? You start from the normal image of the sky, of the cube or not a cube, and you wrap it around the sphere. Okay? Not including too many details, same deal once you are looking at it. It's like, it's a sphere if you think about which transformation you have. I don't want to go into the math or what is a transformation that will take the 3D world and map it into a sphere based on the coordinates, and then taking the sphere that has different topology and map it into, eventually you are just providing a normal single 2D image at the end of the day. Okay. As far as I know, the only advantage for this versus the cube mapping is that you need to provide just a single image. If anybody knows better, make noises why sphere will be better than cube mapping. Okay, yeah. We had reflection, yeah. Environmental map only both methods, spherical and cube, are examples of environmental mapping. Environment mapping. So, okay, cube and sphere and spherical are examples of environment mapping. And yeah, only points that you are rendered and only approximate when things are far, far away. Of course, when you are changing, nothing is. If you are moving, it will not move though with you. Extremely cute topic, and I'm sure that I'll sort a little bit. Because for rough surfaces, you'll find plenty of names. In some part, I guess it's because there is so much industry and people try to stay away from patents by branding it a bit differently. So you'll find the same idea under different names. I try to make some order here, but let's start. What's the problem? I have multiple objects, but I don't want them to look smooth. There is some texture assigned to them. And we'll try to understand better how do we notice this texture. This texture might be just an image. If you look at the carpet, it's completely, it looks kind of two-dimensional. To me, if you look at the ceiling, it's very clear that these plates over here has craters inside them. And I'll try to explain how do you know so clearly that there are craters in them and why is it so visible to us. That there is three-dimensional structure here and much less so in the floor. So we have a 3D description of the surface, and we have a lot of objects. So, what mechanism are we trying to take advantage of is that this part is implemented in hardware and is extremely efficient. What's happening here? I have a texture, I have a point on the surface. I want to, the texture is an image, consists by the way of texels, T-E-X-E-L. A texel is just a pixel of a texture for a point P, and I can apply functions like texture 2D, if it's OpenGL, of a point P on the surface, and I'll get the color of this point. Or I can replace P with the UV coordinates. Just to remind you, the UV coordinates that used in multiple occasions already we have XYZ to denote the whole world, but when I have a surface, 2D surface, maybe circular, maybe it's triangle, I prefer to work with a UV coordinate system, so that's my texture. And the mechanism that takes allocate a point barycentric or given as barycentric coordinate or given in world coordinate of the world P, to know what is a RGB of this point P, it's implemented very, very efficiently. Just to remind you. This operation that return the object is implemented very, very fast and in hardware. Problem. We have our surfaces. Some part of each triangle is seen. How do we know which part is seen and how to solve the hidden surface removal, the parts of the triangles that are not seen? We saw several solutions for it. Painter algorithm, not discussed today. We saw ray tracing, Z-buffer algorithm that is kind of ray tracing except that all the rays come from infinity and are parallel to each other. All of them tells you, from the viewer point of view, out of all these triangles, what is the nearest one? Each ray, even if it's the Z buffer, these rays are just parallel to the Z coordinates. For each ray, which object, which one of the triangles, Ti hits, and at which point it is. But now I remember that each object has its 3D structure on top of it. It can be quite significant. How can I create such an image, especially if there is even occlusion in the texture itself? Solution one is make a triangle for each texture or each component of the texture, each bump in the orange, if you need. Make a component. You have now a lot of triangles because each one of the original object contributed millions of small pieces, and do Z-buffer for all the collection of all the pixels, all the details from all the objects. Very, very slow and mostly unneeded. Mostly modulo one case that these methods are a bit short. So how are we mostly solving it? Well, to solve the hidden surface removal, remember hidden center surface removal, each ray, what is the first object that is it, each ray that comes from the viewer, where does it hit? For this purpose, I'll treat each object as being completely smooth. I completely forget about its texture. If it's triangle, if it's a sphere, it's just a sphere. So to find where a ray hits my sphere, I just solve the same quadratic equations that you solved earlier in the homeworks. I completely forget about the texture at this point. Okay. And now, at some point, I realize that this is smooth, but I want it to look like heavy. And what makes it look rough? What makes it look having the details? And to my opinion, I'm not quoting it from any book, from my opinion, there is no chance that you are seeing that this point is a bit further away from your eyes than this point. That doesn't provide much clue. The gaps in the view are minuscule. So how do you know that this part is rough, it has details, or what makes the craters over here so visible? Same reasons. Shadows and shading in general, the fourth kind. Remember, we have that when I have the visible RGB value that is returned, that is needs to be rendered for a point P on the surface is a constant, the color of the object itself. Red would be 100 times the RGB intensity of the light that hits this point times, and this is important, D, the direction from the light itself, times N, the normal to the surface. So it's all about the normals that creates these craters, and that you see an even bigger crater right here. Right, one side of the crater, even with all the lights on, one side of the crater is highly illuminated, one side of the crater is shaded. Why? Because one side of the crater faces the sun, the other side is faces away from the sun. So the ingenious idea here is, let's, for rate shooting, to ask where among other objects, among other spheres, to see which part of the sphere is visible to the viewer. It's a perfectly smooth ball. But to render it at the end, I need to decide what the intensity of the light coming from each point, but the color basically of each point. And for this, I need to fake the normal at this point. I will not use the actual normal. I will not use the actual normal of the sphere. I will use the normal to the sphere, but then I can modify it a bit. And how do I know by how much to modify it? And the modification of each normal, instead of being the true normal, will have to be twisted a bit to be a fake normal according to some directions that can be different for different points. How do I know by how much to change it and by how many directions? That's details that we are going to describe, but we are going to recycle the process of the texture. We will have a few maps that each one of them tells us by how much should I diverge the normal at each point. Again, I'll have a map, an image, except that this image is not very interesting to look at. It is used as a texture to indicate for every pixel how do the look at commands that we saw right here, but the colors that you're getting from the texture should eventually tells you what to do with the normal. And once you have the normal, then you're applying the illumination equations that we used all the time, in particular the they apply the D times N. And of course, if you want to add on top of it, a specular reflection, you'll see that you want, then sure, go ahead. Okay, so that would be the simulation, and there we'll discuss a few methods of how to change the normals. So historically, first idea is computers are slow. I will compute the normals per each point at a pre-processing stage. Like if I think about computer videos, it will be in a pre-processing stage. So for this point, the normal is not exactly going away from the center. It's going away from the center, but default. And that's pre-computed by how much to default. So I need two numbers for each one, deformed by U, deformed by V. U and V are the coordinate system. Deformed by U, deformed by V, that's a normal mapping. And that idea had shortcut. It was not great. It did not look so great. Just again, visualization of the ideas. These are the real normals. The fake normals that are used for the illumination would be the real normal plus I'll squeeze out from the map, the picture, and the position dot UV, the UV coordinates. I just need two numbers. Let's store them as a red and green coordinates of the texture. And that will tell me how to change the normals. Again, nice in theory, results were less than satisfactory. So normal maps was very soon replaced by bump mapping. And bump mapping is much more common and much more successful method. And it says, you know what, I'll actually give you the whole 3D information. I'm not going to give you the normal, I'll give you the whole 3D information, but it's 3D information provided that for the sphere, I'll say, this is a real sphere. I'll assume that the texture at this point is some deformation, the values that I have right here, is some deformation D that tells me go inside or go outside a bit from this. So the new surface is living somewhere here, but I'll still assume that it's very much a sphere, just not a smooth sphere. That is, my technique will not be happy with something that is stopped being a terrain, stopped being a function of just a location. If I have for the same point a few nuke and levels of the sphere, then it is not captured by this method. It will be simpler if I draw it in 1D. If instead of sphere I have a triangle, a plane, this would be the 0 level of the plane. And what do I give as the bump map? I'll give the texture where I only use one number, and the single number tells me by how much for the point Pi, by how much should I push Pi down to create the real surface. Fair enough, and that can be different for different points Pi. That should be different for different points Pi. What do I mean by being a terrain, being a function of x and y only? That for every x and y you just have one point where the surface is. It will be even more important when we'll talk about the relief map next. Okay, so bump map is more popular, but it takes much more computation. You have more slides that I will not fully discuss. Essentially, that's a sphere. Here is a bump map. By how much should the corresponding point be inserted into the 0 level, the base level, if you wish. Okay, but now how do I compute the actual normals? Help. At the end of the day, I need the normals. So it's not a number that tells me take the normal and divide it by 3 degrees. I really want to, I need now during the rendering for this point Pi to know that this is normal vector in 2D vector on the UV coordinate.
You'll need to take a derivative of your bump function.
Yeah. So from the real normal, I'll ask, here is the bump map for every U and V, by how much you deform U and V. You'll compute the new value. What is B of your V, the bump map? It tells you go in the normal direction, in the plane, in the sphere, so go in the normal direction, but your actual surface is deformed by what you have here in the image. But this is for every pixel, just one look into the array, one texture command to know what is this value. And now once you have the new normal, the new surface, then you need to create for every point its own coordinate system. You'll have the derivative by U, derivative by V, takes their cross product. derivative by u. Here it's just one direction, so I'll take the derivative that will give me this direction. I have another direction over here. They generate yet another vector, take their dot product. Now I have the normal ni. Okay. And I'll take their cross product. If you like, if you enjoy the, yeah. So, and it's more reliable because what? Because it could be the same bump map, but this whole orange lies in different location and X, Y, Z. So, arguably much more, and all these calculations of computing the normals are done during rendering time. Much lower, slightly better variance. Anyhow, that's a norm for bump mapping. But notice that no matter how I look at the sphere, this method that just changed the normal, at the end of the day, I still think that the point that the light is, I still think that if the viewer, that's a ray from the viewer, that's a pixel pi, and with the Z buffer or ray tracing, that was a point that my ray hits the normal. I only playing with what is exactly the color at this very point. And to know what is the color at this very point, I'll actually think about I'll generate the fake normal based on the actual normal over here, and that's just changing the shadow at this point. What I don't generate in all this method is, let's zoom in into more dramatic roughness. Here are these three teeth that are on the surface of the sphere or the plane, and here is my ray, and this piece will never occlude any portion of this piece. It still looks completely flat. Think about it, it's all computer, it's all video games related. The player moves, you expect when you are very close to the Utah pot to have some of these bubbles occludes portion of other bubbles. It doesn't happen, not with normal maps. So what will work? The relief maps. And again, you'll find similar techniques with similar brand names and different providers. So let's talk about quicksort. How does quicksort works, the inner of the quicksort? You have one list that is sorted. You have another list, L2, which is sorted. And you keep two pointers, one from here, one from here. You pick the smaller of the two numbers, spit it out if you are actually sorting, and move this pointer a bit further. 5 versus 9, 5, now 9 versus 17, 9 will progress, and so on. So you have like two pointers, and you each moment, each step, you're progressing in one of these pointers. One of these indices are always increased, depending on which is the two smaller ones. What is the relief mapping doing? Well, we are doing ray tracing, actually. But it's ray tracing very exactly. I shoot from the viewer array. My scene, my geometric scene consists of multiple spheres. I already picked that this ray hit this sphere. So the ray tracing or the hidden surfaces does not happen with respect to all these spheres. it happens only on this sphere, and even not with respect to all these bubbles, all the details of the sphere only. I look at what happens where my ray hit the sphere, what is the first object, maybe the next, and after a few I'll stop no matter what. What do I do? I have the 0 level. This point is where I determined that the ray from the viewer hits the surface that surrounds the teapot, the outer layer of the teapot, the 0 level. And from this point, from the viewer, highly exaggerated, what is highly exaggerated is that think that it's mostly useful for glazing angles. This partial occlusion, these bubbles are very small. And look, if I'm looking at the teapot from this point, not from glazing angles, but I'm looking from the normal to it, then everything that we just described as a normal map, bump map, is fine, because there is no occlusion between one bubble to another. That's where I'm using that it's really a terrain. That for every point here, there will only be one point where you're moving from the normal direction on the real surface. You're noticing this partial occlusion only when, let's see, I'll notice it in this box only when my viewpoint starts to be almost tangent to the surface of the, almost tangent to the surface, and then the partial occlusion of one detail to another starts to play a role. So this ray is a bit exaggerated. It hit my first point, and now I start asking, let's start tracing this ray on the terrain in the direction that it comes, and ask, hey, did I hit the first element? Did I hit the next one? Did I hit the next one? How do I know what to do among the surfaces? Well, this is just sorting. I'm just checking one after the other until I hit in the linear order, just like in the quicksort. Did I hit the first bubble? Did I hit the second bubble? Did I hit the third bubble? And that's it, until I find the one that I hit. So the first bubble, it might be that my ray passes the first bubble and hits the one that comes next, or hits the one that comes next, but other ones after that. I don't care, I just check a few of them. So that's the first trick. And then it goes a bit further, yeah.
I think that was a merge sort, not quick sort.
And you're absolutely right. Wow. Okay. About merge sort. So there is one trick that makes it a bit even quicker to do, and that's if I give you a point inside the surface, if I give you one particular point, I can assume that at some point I'm below the surface. It's an assumption, it's not always true. But I'll assume that my ray is mostly outside the surface, and then it's all inside the surface. Sometimes I can make this assumption, sometimes not, and I want to find where did I move from one step to another. That is that this case that my ray hits the surface, but I still care about what happened to the ray after that. It's not really relevant. It's not that type of hidden surface that I need in this case. So just to ask for each point, are you below the surface or not, if I tell you the point. So I'm not really tracking the point in continuous way as t goes to infinity. It's not the type of ray tracing that you did out there, and that's slightly the information. You can do exactly increasing t, but you can also do for this way, if I'll sample the pixel, for this point, above the surface or below the surface. For this way, this particular point, what do I know for this particular point? What does the relief map tells me? Tell me for this point, what is this height among the 0 level? For the ray, I also know its height. It's above the surface, no problems, go ahead. But now let's take another point above or below, still above, for this particular point. Just one look ahead. There is no calculation of really assigning a plane, what you did in homework 1, of assigning a plane here, asking where the ray hits this plane. It's all way overkilling. We don't want to do it. We want to all generate a few points for each one of them. Look at the corresponding pixel. Are you above or below the surface? And once you find a point that is below the surface, you're done. Then you know where the ray hits. You can do some kind of binary search, again, various level of details if you want to find where is exactly the point that you hit. But you definitely don't worry once you find a point underneath the surface if it's the first point or not. And that's how you generate the relief map, very, very high level. Just very local and very simplified ray tracing where it's the vicinity of where the ray from the viewer hits the 0 level, the reference level that surrounds the whole teapot. Okay, and then how you create a much more dramatic effect. So the light beam. The scene with, so the whole sidewalk here is just one plane, one or two triangles. Normal map, sure, you see that the normal here are normal here pointing to the light, including even the specular reflection that is played on all the top of the surfaces. You see the boundaries between the bricks, but have no clue how deep they are. And look much more synthetic. Then here the light obviously is coming from more or less where the projector is, and you see that the correct side of each brick, first that this brick occludes a portion but not all, this brick occludes a portion but not all of the next brick, and secondly that this portion is highly illuminated because it's reflected to the light, and even adding some specular effects at the side of the brick that faces it. And of course that will change, this relative occlusion, this will change as you're moving. So maybe I'll get back to these topics because it's popular, it's cool, it's a lot of game designs that use it in various ways. Very cool. And again, ray tracing is only once you will see that your ray hits a sidewalk, no question about is this ray continue to do anything below the sidewalk. Same image, zoom in, same deal. Okay. And you'll find similar techniques with nuances that I might get back to about the differences between parallax map versus the relief map. All tricks about the ray tracing and approximate the ray tracing. Okay, just to mention other buffers that we didn't have. We have the depth buffer. Sometimes you want to use accumulate buffer. WebGL doesn't seem to like it, as far as what I can find. OpenGL definitely likes it, the hardware likes it, meaning you can have two images and for every pixel sum up these two images, which you use, for example, in, help, do you have it? Do you have an example here? You'll use it in many cases, but you have various applications, but the first one that comes to mind is actually if you have two triangles that are semi-transparent. One red, one blue. What is the overall color is some combination of the red and the blue. Right. And it's also very popular when we'll talk about Gaussian splatters. Then they made wonderful usage of accumulating buffer. And you can also use it for anti-aliasing. Take the image once and then multiply this image by 1/10. Move the image by quarter of a pixel, multiply by 1/10, and sum them up. So every pixel get contribution is like the average between it and its neighbors. That would be anti-aliasing effect. You can generate motion blurs, depth of field. Makes sense to everybody that we played with this when we talked about application of ray tracing, right? That what I'm looking at is I can adjust my eye so the focal of my eye fits the region that I'm looking at. That's why if I'll show you, if you see the reflection, sorry. You see the reflection of the lights over here, but it's not too annoying. It doesn't really disturb the reading that well. Over here, if I'll write on the whiteboard, this projector doesn't affect so badly, but if I'll take an image of it, if I'll take an image of it and try to read from the image, it will be extremely annoying. Again, every specular spot that comes from the light will be really, really annoying. So how come in what our eye is doing much better than in the image, in the zoom directly, is of course that we can adjust our eye to look at things that are at a distance from you, the distance of the whiteboard. What is the distance from you to the projectors? It's this plus this, the reflection. Further away in the background, your brain, your eyes, put it as noise. One of the properties of our eyes, that we can concentrate on things that are closer or farther without changing the directions that we are looking at, but with changing the focal length. So, and to create it artificially, to create your attention to it, we talked about it, you're just moving the image, moving a few copies of the image, and basically doing convolution with Gaussian. Convolution, smoothing operations that we'll talk more later. Okay, so there is accumulating buffer that you can use, again, easier with WebGL, GLSL. And so on, accumulating buffer, motion blur, sorry, I forgot about this slide. Yeah, soft shadows, one thing that you can, okay, back to texture. I have an old project I'll show you some point of how to remove the specular light from the projectors that are so annoying as we said in Zoom and pictures. If you have two cameras, like stereo cameras, then there is various matchings and white source separations that can allow you to decide what comes from what based on the distance from the viewer, basically. Okay. So we have a texture of the satellite, image of the satellite. And it's only a portion, it sits on a billboard in my scene, and it's very detailed. But if it's very detailed, like have a lot of pixels, but it's very far away, then I don't need so many pixels. I'm wasting a lot of time on retrieving an image with a lot of pixels, and at the end of the day, just sampled the image in only a few of them. That's where the issue starts. Our next topic is MIPMAP, by the way. So that's where I'm good. So it's wasteful to keep the whole image if I'm going to use only a much smaller image. But on the other hand, I might have this image and now the viewer change its location, and now the viewer is much closer to the satellite, and I do need all the details. So the ideas of level of details that we'll mention, and we mentioned in respect to quad trees. So the idea of level of details is that just the idea of level of details says, should I store this very detailed model, or should I get away with the much smaller details? Answer, both. Store this and the much smaller details, and in general, power of 2 is a good strategy. Store the full detail, full the image, and now take it with resolution of half, or that is get rid of quarter, make it half by half, many pixels, store it, and store this one, and store this one, store this one. Which one should I use when I render? Now I can pick out of, in general, it's log n, many levels. I'll pick the one that fits the viewer point of view. Like close viewer, I'll use very detailed. Far away viewer, I'll take much smaller one. Essentially, I want to know how many well, if I start to subsample, I'm start to missing pixels. Like, what's the problem of this picture when you are looking at it far, far away? Think about your camera that have only 10 by 10 many pixels, say. So you are sampling this image at most 10 points. But if you're far, if the satellite is far away, these 10 points out of the higher resolution could be quite arbitrary, running into aliasing problem. We are sampling an image in a not sufficient resolution. So there are aliasing effects that are even more noticeable. That's a classical example that will come up every time that you Google for anti-aliasing and texture. So what do? I have the image. I have the image of this person, and I want to tile. I hope that's the right word. I want to tile the whole billboard with this person, and I can definitely do it by placing these many copies of this person. It all happens in WebGL, OpenGL automatically, that you're tiling the whole parts with a much smaller image. So far, so good. No problems. So I have a small billboard, I have a small chessboard, sorry, and I tile this plane with this small chessboard. But now, the same chessboard that I have, maybe 3 by 3, what happened to it when it's far away? Remember, you have only these many pixels that you're sampling. So some pixels, we saw this example with a building with the red bricks. Some places you have more pattern. Some lines over here that, remember, the original image is just copies of a chessboard all the way, and this chessboard is perfectly fine with all the squares fine. There are no curves out there, but it looks like there are curves. Why? Because we sampled 8 pixels. So how can we, everybody sees it? These fake lines, fake curves that pops up. And the reason that it pops up is that there are only, I started from a chessboard of, let's say, 100, let's say 100 by 100, but when I take this chessboard, placing it here in this plane, and now my viewer is far away from it. Given that this plane is, so I placed copies of the chessboard on this face, but you're all watching this face from this direction. So some of these pixels shows clear and nice because they're close to you. Some pixels over here, some copies of the texture over here far away are infinitely small and close to each other, and obviously your pixels don't do justice to them. But we know that aliasing techniques can solve these artificial. Aliasing, for example, take every pixel and average it with the nearby pixels. I can replace it with averaging it by the nearby pixel, points that are far, far away. Great, I can do it in real time, but it will take lots of time. Well, if I know that there is a chance that I'll try to tile a surface with this pattern and I'll have plenty of copies and it might be a problem, why shouldn't I put these multiple copies, the person if you wish, the chessboard if you wish, put these multiple copies in the pre-processing step, do the anti-aliasing before you're using these textures at all. So don't put all the copies and then do the anti-aliasing. Pre-process one texture image with multiple copies and anti-aliasing already done. And both these directions leads us into MIP-map. So MIP-map says I want to have this texture, but I want you to store it using level of details, that is stored multiple copies, and as you are storing these multiple copies, please do the aliasing if needed, if there are multiple copies out there. And you'll just tell OpenGL, use MIP-map, and give some parameter that even says when you're doing the anti-aliasing, how should I define what the P, and the anti-aliasing is again, store not necessarily this image, but this image multiplied many times, but on much smaller resolution, plus the anti-aliasing. So how do I do the anti-aliasing? I take every point, and what should I do? I can replace it by, which way did we assign value to pixels? How did you decide in homework 1 a value to a pixel, a Q based on 4 pixels, P1, P2, P3, P4? We mentioned a few versions. You can use Q as a nearest neighbor. That's not anti-aliasing, that's the default. Just take the nearest center of the pixel. Or you can use a bilinear interpolation based on distances to the 4 corners, or even use trilinear interpolation. Why is the third interpolation here? Again, linear interpolation, because you have interpolation between one layer of details and another layer. So it was a long speech to explain what is MIP-map, but when you're using it, essentially you're just saying, this texture, OpenGL, this texture, use MIP-map when you're storing this texture, and OpenGL will be kind enough to A, generating the different copies, and B, decide which of the copies, which level to use, based on where it is in the big image, without you having to direct it. Fair? You just need to say, yes, I do, yes, I want to use level of details, that is MIP-map, and all these different levels and the anti-aliasing involved in it will be done without you having to interfere, unless you want to. One word about how much memory. There is some waste of memory that I have, because rather than having one image with n pixels. I have one image with n pixels. You took algorithms with me, know where it's going. I have one image with n pixels. That's a full resolution. But if that has n pixels, altogether n, so it's 10 by 10, n will be 100. If that's n pixels, and now here I have only, what is it's n divided, what is it's not n divided by 2, because the number of rows is half and the number of columns is half, so it's n divided by 4 that I'm also copying. And then it's n divided by 4 divided by 4, because I take in the next level only quarter of the level that I had before. And I can add more and more terms, but I can even go to infinity over here. But this number is, it's less than 2. So I'm storing less than 2 times n, if you want to ask. Exactly the overall part here will be n times 1 over 1 minus 4, which gives us, am I right? 4 over 3. Check me out, but this additional memory that you're wasting for keeping all the level, all these different images in time, instead of storing n, you're storing 30% more than n, but then it's make your rendering process so much faster because you're picking out of all these images the one that fits you best. And the idea of level of details that we mentioned in Quattro is very popular. It says, like, here is a Stanford bunny with these many triangles or quads. Here is a bunny that after simplification where I only have 2,500 many polygons. Here it is with only 251, and here it is with only 36. Which of the bunnies should I use? Depending on where the bunny is in the overall scene. On the fly, I'll decide where it is based on the angle that I see it and what's the point resolution, right? I don't need a highly detailed bunny if I only sampled the pixel. If I only sampled 5 pixels in the whole bunny, there is no reasons to keep these many polygons. This will do just fine. So if I'll ask you in the final what's the basic idea of level of details, so it's Stanford bunnies. Yeah. Next, we are talking about more examples about the what happens to structure, to texture under perspective, and why do we need the aliasing, and why the aliasing is so clear. So that's the image that I expect to see. I have some little texture that appears many times all the way to the horizon. So, and without anti-aliasing, that's the result that I see. Instead of nice rows of this field, total noise. And yeah. And it's already annoying as a static images. If the camera moves, then all this blinking out here completely highlight that something very wrong happens. Why? Because I don't average each pixel with the neighboring pixels. So the flickering of pixels from blue to white is very noticeable. And just to explain why it happens, here is a texture, here is a pixel of the viewer image. What do these pixels take from the field when it's far away? When you're looking at parts that are close to the viewer, do you have an example? When I'm looking at parts that are close to the viewer, I don't have this example, it will be more or less a quadrilateral, but a nice, fat, close to square quadrilateral of 1 pixel over here. But the very same pixel, when it's far away from the viewer, what you actually, this pixel cover, is the shape to the field that looks like so. So you're averaging a shape that might happens to contain only the corner, so it's much wider, or contain only the line, this pixel over here that happens to contain only the line, or can take something that has nothing to do with, if here I have in the original shape, I have say 5% blue and the rest is black, a single pixel here might be way biased to be completely blue, completely black, depending on the shape of the pixels. And that's why the more scenario happens. Right? So that's what will happen. That's how it will look like without MIP mapping. And with MIP mapping, well, you saw how it looks with MIP mapping. With MIP mapping, you got the field nicely out. So do use it. I think that's my slide. Yeah, next is quad trees and R trees and hashing as accelerated structures that we have. People in computational geometry will find it will not find much newer stuff about it. It will be quad tree. We'll just talk a bit more about how to do ray tracing. But if you know this material, then bring something to it. Questions? Okay, thanks. Go on.
No theoretical on homework 4.
Sorry?
No theoretical question on homework 4.
No.
Okay.
It's also much simpler than I planned. I decided that I wanted to have shadow, decided that shadow, especially in WebGL, not smooth enough. Yeah, let's take it simple. Yeah, that's why it's I estimated that this time should be enough. I don't. Yeah, as usual, make noises if the time is too pressed, but I thought that this time is reasonable.
Hi. I was wondering if there's a time I can schedule.
You don't read Piazza.
Huh?
You don't read Piazza. I sent an email. Piazza post. Don't want to give you a hard time. I sent a Piazza post of what to do if you miss the so we are thinking about Wednesday. Maybe
okay.
Maybe 12. But let's see. So far there are 3. You're 1 or 2, 3 people.
Okay, cool. I just want to make sure I'm not holding up.
I mean, I can negotiate other time if it's bad for other people, but that's where it's going. And about location, I don't know. We'll start in my office and I'll sprinkle you of a few other rooms, or I'll secure one of them in the department. I'll figure out. Let's see that it's indeed that Wednesday 12 works for everybody.
Okay, cool.
How was the race?
Oh, it was crazy. You can see all my numbers on my arm. They just put tattoos on us, give us our race numbers. But I did 3 races.
No RFIDs?
No what?
RFIDs, no chip in the
Oh
shoe?
yeah, we do put chips around our ankle, but this is just for like identification, just like during the race. So
okay. And which race?
It was collegiate nationals. It was in Miami. Triathlon.
Triathlon. Okay.
Yes.
That's I understand. So full marathon.
That's so I did. So there's different distances. So this weekend I did a sprint distance, a super sprint distance, and Olympic distance. So the Olympic distance is a mile swim, 40K bike, and a 10K run, and then the sprint distance is
10K.
You did all 3?
Yeah, I did
did all
3.
3
I know.
races?
I was so tired at the end. But I actually did.
Wait. You said 40K bike and 10K run.
Yes. Yeah.
Bike is less than running.
The other one, and then
Oh, bike is more than running. 4D, 40K bike.
40-kilometer bike,
yeah.
so it's 22 miles or whatever.
So
and 100K running.
Oh, 10K. So
10K
it's it's
run.
about
Okay,
6
that's
miles.
yeah.
That would
Okay.
be crazy. 100K run. Yeah. It was fun. So 15th in the country.
Holy shit.
Yeah.
That's actually really insane.
Thank you. Thank you.
I wanted to ask a couple questions.
Sure.
I started crying notes. So I was looking at what I did on the midterm.